I need to get my, good. We got the infinite screen. Excellent. What's NeuroMANCER?
That's the library that I will be talking about today. And
good. So that's why you have that as a background.
Yes.
That's Metal Rock.
And there's also a wonderful sci-fi book by William Gibson.
Oh, by who?
William Gibson.
Oh, I don't.
That's one of the foundational sci-fis in the cyberpunk genre.
Oh, okay. This is so familiar. I never read that. Wait, is it just a novel or is it a movie too? Right?
Novel. It's a novel.
Yeah. Okay. All right. Well, then let me also log into something. I take notes during these talks to make sure everybody has like a good summary before they, get into an area. But I think now we're getting a quorum. The people are on the stream. Thank you. Yes. Okay. Cool. Excellent. So let me just start the recording and I give you a very brief intro, and then we'll start. Oh, that's your library. Cool. I'll make sure to add a link to it. That's a good one. All right. Cool. So let me do the recording. All right, cool. Well, yeah. Hey, everybody. I'd love to introduce young Drgoňa from PNNL and upcoming Johns Hopkins. So you've been doing a lot of cool work on differential programming and application for control and various kinds of, physics from the ML. So welcome, Jan.
Thank you very much, Greg, for the invitation. It's a pleasure to be here. And thanks, everyone, for joining and finding time today to listen to me for an hour. I'll be talking about differential programming for modeling dynamical systems, solving optimization problems and controls. And I decided to be a little bit more hands-on and show some coding examples that we have in our library that we call NeuroMANCER, rather than going through just papers. So if you have any questions during this talk, feel free to stop me anytime and we can make it more interactive and have a discussion. So I'm currently with
Jan,
yes.
Do you mind clicking hide on that thing?
Oh, sure. Yeah. Perfect. Thanks. Good. So I'm with Pacific Northwest National Lab in Physics and Computational Sciences Division, where we are working on modeling and control of complex systems, primarily in the space of US Department of Energy, whether we are talking about power systems, wind technology, or buildings, or transportation networks. Very often we have high fidelity simulations of those systems, but they are prohibitively expensive and they are not suitable for closed loop decision making and control. So traditional control methods are not very suitable with this. And we need to revert with sampling based approaches like deep reinforcement learning, but they don't really scale that well for these type of complex systems. So there are several challenges when it comes to this computational aspects, but there is a promising trend of combining machine learning with physics, so-called scientific machine learning or physics information learning that inspired our research area. So one of the challenges is that we are dealing with heterogeneous modeling methods. When you have these high-fidelity simulators, they are often called also digital twins. They are typically component-based white box models that are implemented either in MATLAB Simulink or in Modelica languages or other custom environments like Energy Plus in building space that are not differentiable, that are heavily abstracted in terms of the visibility of all those physical equations. So you cannot use algebraic modeling languages that we use in optimization control just to embed them as a constraint. So it's just simply technically not possible. So traditionally, we are using black box approximations or gray box models that are reduced order and simplified, very often linearized in terms of gray box modeling. But for each of these, we have different tools. Yeah, we have algebraic modeling languages for these linearized and simplified gray box models, and for black box models, we often use deep learning libraries. And when we have model representations of our engineering system, we are dealing with heterogeneous solution methods, depending on what type of problem we are solving. For instance, if we are solving economic dispatch or optimal power flow problem in power systems, we are dealing with constraint optimization, or if we are dealing with model priority control in real-time optimization, that's constraint optimization algorithms that are providing us with the solution. And traditionally, we need to know the objective function, we need to know the constraints, so we can use some iterative solver, whether it's active set methods or interior point methods, to obtain the solution that satisfies certain constraints. Similar story when we are dealing with forward simulations of differential equations. We need to know the right-hand side of the differential equation, and then we use some numerical solver, like Runge-Kutta type family method, or finite element, finite volumes in PDEs to obtain the forward simulation. And in machine learning, the paradigm is different. We are having some labeled data sets for supervised learning, or some environment that we can sample and obtain scalar-based rewards to learn actor and critics in standard reinforcement learning. Usually there is no physics, or physics is hidden implicitly in the system environment or in the observation of the data. So this led to separation of tools in engineering and machine learning. So when we are solving constraint optimization problems, we are typically dealing with algebraic modeling languages or frameworks like PyOmo or CVXPy, JUMP in Julia, and more specialized for optimal control like Gecko or Casadi. I don't know whether there is someone who has background in controls and operational research, but if yes, then you're probably familiar with these software tools. And in differential equations, like you are using MATLAB, Julia, or Python ecosystem for numerical solvers, or some domain-specific solvers for power systems or molecular dynamics that are tailored to those particular physical systems. Everything is model-based. All the physics needs to be known beforehand in this category of application areas traditionally. But really, what revolutionized most of those areas of engineering and science, like 10 years ago, was the accessibility and user-friendliness of deep learning libraries like PyTorch and TensorFlow, and new libraries that emerge like Flux in Julia or JAX that are very easy to use. And first and foremost, they are allowing you to implement differentiable models. So you can use first-order gradient methods to optimize not only neural networks these days, but really complicated computational graphs that can represent implicit layers like differential optimization or numerical solvers for differential equations, like in the case of neural ordinary differential equations. So what we see is a convergence of machine learning and operational research or traditional applied maths and controls communities to develop new algorithms and new software tools that are called scientific machine learning or physics information learning, to systematically combine deep learning with traditional process-based or equation-based models and the numerical solution algorithms. And why we want to do that? Because in the engineering applications, we have some prior knowledge about the system. There are some governing equations that we discovered in the last several hundred years, so why to throw them away when we know that they are conservation laws? Why not to impose them into the system and reduce the degrees of freedom, or obtain some safety or constraint satisfaction guarantees that are very important in safety critical systems like autonomous driving, for instance. So all of this is enabled by automatic differentiation, which is really like new software tools democratizing already existing frameworks and tools that have been here for decades. And here is just very biased, incomplete literature sample, papers that influence my thinking and my research, like differential programming seminal paper by the Julia community, or physics informed neural nets that are used to solve partial differential equation by sampling the collocation points in the parametric space, which are very related to so-called learning to optimize methods for end-to-end training of neural networks to solve constraint optimization problems applied to operational research applications like power system optimization or transportation networks. Then we have learning to model area, where we are learning neural operators to approximate dynamical systems. And this can be purely black box, like neural differential equations, or gray box variants like universal differential equations, or Koopman operators, Fourier neural operators, all sorts of variations of sequence-to-sequence models through neural operators. And then when we have the capability to impose constraints, learn dynamical system, then we can combine these into control. So there are different ideas how to differentiate through model predictive control, optimization problems, or how to use differentiable physics to train control policies for particular systems or any dynamical system in general that is differentiable. So these are the ideas that inspired my research and of my colleagues at PNNL. And we asked the question, can we come up with unifying algorithmic framework, so when we implement these methods, we don't need to start from scratch? Because very often when you read those papers, they may come with open source code, but it's one of implementation, and it's not as easy to integrate, let's say, learning neural ordinary differential equation representation of your system with learning to optimize implementation from other paper. So we have been thinking hard, what are the primary components? How can we come up with abstractions that can serve all of these modalities? So first modality is, of course, there is some sort of data acquisition or active sampling that we are dealing with in these scientific machine learning methods. And they can be either observations from some physical system or some sampling of collocation points in a parametric space. Then there is some machine learning function approximator. Can be simple multi-layer perceptron or more advanced architectures like graph neural nets. Then there is some form of domain prior, some physics that we know, some partial differential equation that we want to impose, or some safety constraints that we want to project onto, or some dynamical system equation that we already know from the engineering research. And then you have some domain-aware loss function or physics-informed loss functions, where typically we enforce the constraints in soft way by penalizing those violations. And there are different ways how to technically implement it, like penalty methods or barrier penalty functions or augmented Lagrangian. So like there are a lot of different varieties in these four components, but we believe that these are the four primary constituting building blocks of any scientific machine learning framework. And to give you some example to make it a little bit more tangible, let's start with PINNs, physics-informed neural networks. That are probably the most famous example of PIML methodology. So you start with sampling the collocation points in the PDE domain, which is typically spatial and temporal coordinates. So here's a simple example on two-dimensional problem, one spatial, one temporal coordinates, and these blue dots represents collocations in this space-time. And at each of these points, which is scalar value, we are taking this as an input to the neural network that generates the candidate solution for the PD equation. So this is the function approximator here. And this candidate solution is evaluated through this PD equation. So we have this physics-informed layer for which we need partial derivatives of the neural network with respect to the parameters, space and time. So this is obtained by automatic differentiation. Very easy to implement in PyTorch or TensorFlow. That's why it's so popular. Anyone can use it very easily. So this would be the domain prior layer. And then you have loss function that is minimizing the residuals over the collocation points. And in this case, this PINN PD equation needs to be equal to 0. So we are just minimizing the residual of that. We want to push this to 0 by minimizing this expectation of the violation of these equality constraints over some sampled collocation points. Very often we have also some supervisory loss function over initial and boundary conditions. There are these red dots. So that's standard supervisory loss function. And then you combine them together, and that's your PINN trivial standard PINN approach. There are way more extensions where you have like adaptive weighting on these loss function terms or additional constraints, or training multiple neural networks in a residual architecture for multi-fidelity physical systems. So there is a very active research in this area that allows you to solve a range of physical modeling problems, whether it is training neural network to solve partial differential equation. In this case, this like the diffusion process that has been trained by NVIDIA modulus, and also parameter estimation problems. So you can combine data with some prior physics to estimate some unknown parameters in your PDs. So very popular approach these days. And why it is popular? Because first, it's very easy to implement and train. There's still a lot of open research problems in differentiability, convergence, and scalability. But once it is trained, you are obtaining explicit solution to complex physical problem that requires a lot of computational resources with traditional numerical methods, like finite element methods, would take orders of magnitude slower compared to neural network that is trained. So that's really the promise of the scientific machine learning methods. So once you train them, you have very accurate and fast surrogate model of physical system. So next method that I mentioned is so-called learning to optimize. Conceptually very similar to PINNs. And here is why. Because we are dealing again with sampling the parametric space of constraint optimization problem that is given by some objective function and some constraints that can be in general nonlinear. And here we are using the neural network that takes the sampled parameters that are denoted by psi over here, and returns the primal solutions that are denoted by X. So take sampled parameters in, generate primal solutions that now, instead of satisfying PDE, we want to satisfy this inequality or potential equality constraints of the optimization problem while minimizing some objective function. And examples can include like power system optimization, or like knapsack problem, just some of the examples. So how can we enforce these equality, inequality constraints in other way, just by like sampling and simple penalty methods? Because feasibility is very often more important requirement in the operational research than necessarily the accuracy or optimality of the objective function. So there is a lot of active research in so-called differentiable optimization solvers or feasibility restoration layers that allow you to project the solution that is generated by neural network into the feasible region that is defined by the constraints. So there are a lot of technical details behind it. There are different ways how to implement that.
So question.
Yes.
It seems like now the job of previously the PDE's job in that slot was to say, given what the neural network is producing, it's a good solution versus a bad solution. It was kind of a checker. This seems like it takes a solution and says, it's not optimal, but starting from you, I'll find an optimal solution. Is that valid?
Yeah, it approximates the optimal solution. It's because these are first order gradient methods. So very often, like when you are dealing especially with non-convex optimization problems, you are not guaranteed to converge. But the advantage of these first order methods that they will allow you to train large models relatively fast and obtain approximate solution that once after it's trained will be again orders of magnitude faster than solving this with interior point methods or active set methods.
Okay, so this solver is not one of the expensive optimizers. It's a cheap optimizer.
Exactly. So for instance, this projection, you don't want to have fully fledged optimization solver as a layer. That would kind of defeat the purpose. You can do that if you want to tune that solver with end-to-end training, for instance, like training the time step over there or some weighting terms in the constraint penalties. So there are some papers that are doing that. Example would be that this differentiable convex optimization layers is basically a wrapper for CVXPy, which is one of the popular constraint optimization libraries, to differentiate through the conic solvers that are implemented there. Okay. They allow you to embed any convex optimization as a layer in this end-to-end architecture.
Got it. But even then, you're only doing it a few times. Like you're training a climate model circuit and climate model traces. It's expensive.
Exactly. Yeah. It's always a trade-off. Like I see there's a spectrum now because we have these software tools. We have either full numerical solvers for differential equations or PDEs, and then we have just black box function approximators when we have tons of data. Anything anywhere in between, you can have only part of that solver implemented as a correction layer. An example would be like augmented Lagrangian method. There is very simple fixed update rule for the dual variable that is updating the weighting terms in your penalties on the constraints in the loss function. So yeah, there are different ways depending on your application. Yeah.
Yeah, got it. Thank you.
So what can you do with this learning to optimize? Well, I mentioned optimal power flow. That is like very popular in operational research and in power system community. A lot of active research in this learning to optimize is done in those like papers, automatic transactions on power systems. And a lot of research is done in so-called feasibility restoration layers, as I mentioned. So like your neural network, if it is like not trained properly, like you want to project the solution to some feasible region. And I also seen recently implementation of those ideas in generative modeling in stochastic neural differential equations that define that generative process for score-based modeling. So like a lot of interesting ideas that are originating from learning to optimize could be applied to more like traditional machine learning applications. Another category of approaches are neural operators. And here is an example with neural ODs, where instead of sampling the collocation points in PDE space or optimization parameters, now we assume that we have observations of the time series data. And this could be climate models, or it can be temperatures in some heat transfer model, or it could be velocities, accelerations of some kinetic model. But we assume that, okay, we have some rollouts, and we are going to chunk these rollouts into sequences of the finite horizon length, and then we are going to design some differentiable system representation. And this could be just neural ODE, where right-hand side of the differential equations is approximated by black box neural network, or it can be a gray box model. You don't necessarily need to have purely black box model here. It can be some structured equation, and neural network can approximate only some subset of the parameters of the ODE. You can also use like this neural operator approach, like Koopman's, where the neural networks comes in the picture as this encoder-decoder architecture. They call it like basis functions or lifting functions from the observable space into latent space, and in latent space you apply the linear transformation. In Fourier neural operator, these are Fourier transformations, and then you have linear operator in latent space. So there are a lot of examples, and there's like a whole zoo of architectures that allow you to do this dynamic systems modeling. But typical loss functions are to penalize end step ahead prediction error on those rollouts, and you can add additional penalties like approximating the finite differences if your signal is not noisy, and additional regularizations for the sparsity of the neural representation, or many more. So what has been already mentioned, like climate modeling is one of the premier examples, which is super expensive to solve with traditional numerical methods because it's a very high dimensional problem. And these Fourier neural operators have been successfully applied in this. So it's, again, credit to NVIDIA research group. These models are also more and more being used in system identification of engineering systems and for the purposes of design of control. So how can we design control systems with these models? If you have differential equation that is learned from data, you can use model predictive control, which is a strategy that transforms the optimal control problem in optimization problem, and then is using optimization solvers to obtain the control action. So it's so-called implicit control policies as opposed to explicit control policies trained by reinforcement learning, often parameterized by deep neural networks. So there is also another category of methods that is called learning to control or differential control, that is kind of combining reinforcement learning principles with model predictive control. And again, conceptually very similar to learning to optimize and physicing from neural networks, because you are having some control parameter space, and this can be like initial conditions of your physical system states, or it could be boundary conditions. So it can be a goal parameterizations of your objective function, like what types of reference trajectories you want to track, or what type of obstacles you want to avoid. So this can be all parameterized and embedded as features for the neural policy that is taken as an input and generates control actions. And again, it doesn't need to be neural policy. Any differentiable function like polynomial basis or linear feedback controller can be trained this way. And then the crucial part is that system model that is differentiable, and it allows you to propagate the optimal control function gradients through this system dynamics backwards. And these system models can be like neural differential equations or just white box differential equations, can be state space models. It could be recurrent neural networks. Whatever differentiable architecture that represents the system dynamics could be cast as this closed dynamic system. And then you can sample those parametric representations of the initial conditions or other constraints variations to train this model on, again, sampled expectations of the optimal control loss functions that is inspired by how we formulate objective functions in model predictive control. This would be equivalent to real-world engineering in RL. But the difference with RL is that now you compute the sensitivities of the objective function through the differentiable system dynamics model and obtain neural policy gradients directly. So you don't need to train any value function, right? The differentiable system model and the parametric optimal control objective represents your white box or gray box value function in this case. That's the difference. Why would you want to do that? If the model is differentiable and has nice numerical properties, then typically this converges way faster than sampling reinforcement learning action in state space. Also, it allows you to embed some control theoretic constraints to project the action space into some polytopic regions, let's say, for control constraints, or it allows you to embed so-called safety filters in controls, like control barrier functions or Lyapunov functions for certifying either constraint satisfaction or stability, which is very important in controls applications.
So, question. But also on the call, is this compatible with live control?
With live control?
Yeah.
I'm not familiar with the term live control.
Well, I guess real-time control is the term.
Oh, real-time control, yes. No, this is offline learning. So in real-time control, you would take the system model and solve the optimization problem to compute control actions. And every time you obtain new measurements of the system dynamics that represent new parametric instance of this optimization problem, you would need to recompute the solution. So real-time control is very powerful. It has been applied in many areas in industrial control and in robotics. If you can afford to compute real-time control, it works wonderfully. but very often we are dealing with computational limitations or resource limitations on the battery to compute these expensive real-time control strategies, especially in systems with very fast sampling rate. So this is a combination of reinforcement learning ideas and model-priority control ideas to learn offline control policies by sampling the parametric space that we expect to encounter in the real implementation, and minimizing the expectations of the optimal control loss function and backpropagating that to the differentiable system models.
But actually, I'm trying to understand the flexibility of this design. So one thing you said, you were differentiating this from RL, but it seems like you can code up RL in this framework just as easily. I mean, I shove DQN as my neural policy, and it's pretty much the same, right?
So the difference in traditional actor creating method in RL that you treat the system model as non-differentiable black box, where you perturb the system, you provide actions, and you obtain the rewards and the current state measurement. And then from these state action pairs, you are trying to learn the value function that approximates the landscape of the rewards as a function of states and actions. In this case, you don't need to learn the value function because the value function is given by the parametric optimal control objective and the system dynamics model.
And tell me if I got this right. The critical difference is you assume your system dynamics is a differentiable, whereas RL does not.
Exactly. So that's the limitation. Everything here, what we are talking about, must be differentiable.
Got it. And one more question. I'm noticing you don't have an arrow back to control parameters, which means you can't do adaptive sampling in any of these schemes, right? You cannot choose your control parameters you try conditional on where your uncertainty is. Is that a real constraint or just?
This is conceptual constraint in this particular slide. There are methods that you could do that in PINNs, and in principle you could do that in learning to control. Yeah, it would be possible. Yeah.
Okay, thank you.
Yeah, really good questions. All right. Yeah, thank you very much. Anything else regarding this learning to control, or?
I think it's good for now.
Perfect. Yeah, so we have been doing some research in this area of learning to control and able to apply it to some simulated robotic systems, and in particular to energy systems. That's our main application area. So we have been doing research on building controls and power systems, where very often these real-time optimization approaches are too expensive, because often you're dealing with larger state space and action space, and your low-level hardware is either not computationally powerful enough, or you have implementation restrictions in this particular application. So you want to have something way simpler to deploy, like neural network versus the full-fledged real-time optimization. So that's kind of overview of 4 different scientific machine learning methods that our team is particularly interested in, that on the first glance, they may look like different methods, like teasing from neural nets, learning to optimize for constraint optimization problems, neural operators, and learning to control. But my argument here is there are similarities between them, and it is possible to abstract them in more generic SIMO framework. And that's the reason why we start to develop the library that we call NeuroMANCER. And if I have time, I can show maybe 1 or 2 examples in the library. I believe it will be more interesting than just browsing through our papers. Okay, so I shared the link to the library at the beginning of the talk. Can I minimize this? Okay, I will hide it like this. When you click on that link or scan that QR code that I shared, you should land in this GitHub, PNNL/NeuroMANCER, where we introduce the library, and it's really motivated by algebraic modeling languages in controls and operational research like CDXPy or JUMP that allow you to formulate symbolic representation of your constraints and objective functions, and then parse this into solver-specific language, because different optimization solvers, whether you would be using Gurobi, Cplex, or some IP opt solver, they would require slightly different formulations. So what we do here, we provide an API to generate computational graphs in PyTorch for these custom scientific machine learning architectures to be trained with first-order gradients, with stochastic gradient descent. So all of those methodologies that I presented are supported. And when you land in our README, you have overview of the table of content, typical like new features in the latest release. But where you get started is, I would say, getting started section, where you can get familiar with the high-level syntax of the NeuroMANCER library and go through examples. But to make things more interesting, I will probably just scroll down and walk through a PIN example to introduce the abstraction. So we went over the PIN, so we have neural net and PDE layer and that soft constraint loss function. In this case, this is a textbook PIN from the original paper. You have diffusion equation, and we know some initial boundary conditions, so we can sample the data points. So I'm scrolling down to skip the code, but here are the collocation points. One temporal and one spatial coordinate. The blue are collocation points over which we are going to penalize the PDs, and the red ones are the boundary conditions that are supervisory signal. So what we are building on is PyTorch. So we are using Torch data loaders to sample from our dictionary data set. So that's something different than what you would have in standard PyTorch model. In PyTorch, you would have some tensor data set. We have dictionary data set where each key represents the symbolic representation of our variable. And here we have two representations of spatial and temporal coordinates, and each has some tensor value associated. So that would be our sample data set. And then we have this function approximator, then neural network architecture. So this can be any PyTorch NN module. So here is just very simple multi-layer perceptron. And in order to make this compatible with this dictionary dataset, we are having this wrapper, what we call node, that takes any callable in Python, wraps it based on the positional arguments on its forward pass, and the return. So if you know that you have two positional inputs in this callable, you can label them accordingly. So in this case, it would be spatial and temporal coordinates mapped into the what we call here y hat, that would be output of the neural network that approximates the PD solution. And then we want to implement this PIN layer. And here that neural network requires computing partial derivatives with respect to the parameters. So we would instantiate these variables, the y hat that is basically pointing to the output of the neural network, and p and x that are spatial and temporal coordinates that are pointing to the data set. And then we can use this grad method to instantiate symbolic gradients, symbolic partial derivatives of dy dt, dy dx, and second partial derivative of dy with respect to x. And these now represent new variables, and you can combine them in this expression to define your PIN layer. Why we did this, why we chose for the symbolic API, because we want to decouple the data handling and the dimensionality with the actual problem formulation. So this allows to have a layer that can be implemented in a batch tensor and in a single instance, because the tensor value in that dictionary data set can be changed based on each run of this model. So now you have data set, you have the neural network function approximator wrapped in the symbolic node wrapper, and now we have this symbolic layer of the domain priorities PIN. next, and you can also like investigate like this computational graph, but it's kind of messy. So the next you want to do a loss function definition. So you want to minimize the residuals of the PIN layer, impose the boundary and initial conditions as this residual between observed and neural network outputs, and you can add additional constraints. Like in this case, we know that this a diffusion equation solution lies in the domain of -1, 1. So like we can impose these soft penalties on the neural network to stay in that bounded domain. And then you have loss function with 3 terms. So typically you would need to have some sort of scaling to make this problem numerically well posed, especially when you have like multi-scale systems or the constraints are in different orders of magnitude. But in this case, this is super simple textbook problem, so the scaling is all the same for all of those. So what we provide is implemented this operator overload approach over these comparator operators that allow you to instantiate these objectives and constraint terms with few lines of code. So like you say, my PIN layer, the output of the PIN layer, the PD equation essentially needs to be equal to 0. And this, I want to have the output of the neural net over the initial boundary conditions equal to those observed. And then I want to bound the neural net within some constraints. So then you have these 4 terms that you can assemble together in this soft constraint penalty loss function. And there are different ways how to do that. That doesn't necessarily need to be just simple penalty. It can be penalty barrier functions or augmented Lagrangian methods or any type of custom loss function that gives you scalar value so you can backpropagate these gradients over the sampled data sets to train the neural network approximation. So we define it as a constraint optimization problem where you are optimizing trainable parameters in these nodes by using the loss function that includes objective function terms and constraints. And this allows you to use standard PyTorch stochastic gradient descent optimizer to train this PIN. We have this custom trainer defined, but we also have examples that allow to use PyTorch Lightning trainer that is more scalable, so way more performant. But just for the sake of example, this would be good enough now. And after the training, what you typically do, you compute the approximation error of your PIN solution versus your exact PD solution. And because this is a super simple problem, you barely see any differences. So like those errors are very, very small. So this is a typical code template for physics-informed neural networks, and there is a lot of research in what type of function approximations you should use in PINs. Instead of multi-layer perceptron, there's been like interesting like Kolmogorov, Arnold networks for more parsimonious representations, or instead of manual design of penalty terms in the loss function, there are some adaptive weight optimization techniques that pay attention to regions in the parametric space that exhibits sharper behavior. So like this, for instance, the diffusion equation is relatively smooth, but you can have shocks, you can have boundaries. And in these cases, when there is this so-called stiffness in this differential equation, it's advantageous to sample the boundaries when you have the constraints or those shock behaviors.
So a couple of questions. So is it possible to use JAX as a backend?
Not at the moment. So we have this in long term to do to support that, but everything was built from scratch on top of PyTorch. So we are kind of heavily linked at the moment with the PyTorch ecosystem. I would love to have a JAX backend, but that may mean that it will be new software product.
And then another one is, how does this relate to NVIDIA's modulus?
Very good question. So NVIDIA modulus is super high performance library for neural operators and PINs. They are more specialized for PINN. So if you want to do cutting-edge research in physics for neural networks and neural operators, I think their library is more extensive in this space, but they don't have any learning to optimize and learning to control. So if you are more from operational research and controls committee, our library will be way more suitable for you. Yeah.
Thank you.
So maybe I can show you some control examples.
Yeah.
You have some time. Let me start with learning to optimize, and then I'll go to control. Yes, so let's start with this super simple one, or yeah, let's say this. Let's say CVX. So here would be example of solving a parametric optimization problem with objective functions and constraints. Theta is a parameter that modulates the objectives and constraints, and X is the primal decision variable. And conceptually similar, but numerically different to PDEs. Very often in PDEs, you want to map like 2, 3, 4-dimensional parametric space into one-dimensional PDE solution. Here, very often you have hundreds or thousands of parameters and hundreds or tens of thousands of decision variables. So it's a way more large dimensional problems in learning to optimize. So one specific example is this Rosenbrock function, that it's very famous test function optimization. The P is the parameter of the Rosenbrock, and we have these inequality constraints, linear inequality in this case, and B is the parameter in the constraint. For the sake of like tutorial, this will be simple 2-dimensional example where the decision variable has two x1, x2 components. So again, you start with sampling the parametric space in the same way like you would do in learning to optimize physically informed neural nets, and then the same way you just instantiate your function approximator, again multi-layer perceptron, then you wrap in this node class and define those parametric instances for the inputs, and it will return the primal decision variables. So the code until now is exactly the same in terms of abstractions to PINNs. What is different here, that instead of PINN layer, we are going to define these objective functions and constraints. So this will be this Rosenbrock function that will be minimized in the framework. And then we want to impose some constraints. We could use penalty methods like I shown in PINNs, but you could also use the so-called safety filters or feasibility restoration layers. And here is example how we integrate with CVX-PI layers, which has been developed by the original developers of CVX-PI. It's from Stanford and collaborators for CMU. That allows you to basically implement the projection that is implemented as this quadratic program, where your neural network is giving you a candidate solution, this X, and you want to obtain the corrected solution, X hat, that is close to that suggestion from neural network, but still remains within the feasible region. So yeah, behind the scenes, what is happening, like you are really differentiating to this canonical COM program, and it's more can be found in the CVX-PI paper, interesting work. So that's what you implement here. This is the implicit layer. You are defining your CVX-PI optimization problem, this quadratic program that will represent your projection, and then you wrap it as a CVX-PI layer. And then that CVX-PI layer we wrap in our NeuroMANCER node class, so it can have the symbolic representation. And then we can combine the neural network with this projection layer to define this list of objectives and list of nodes. And we use the same penalty method overall to train this problem. I use the same stochastic gradient descent through the trainer, and we should obtain some solution that in this particular case is demonstrated as a poorly trained neural network by design, so we can demonstrate that projection layer that corrects the solution to the feasible region.
So question on the call, when you're using this for models of buildings, what is your method for constructing the problem? Do you provide an RC gray box model and have the optimization solve for the optimal resistance and capacitance values?
Exactly. Very good question. So because there is a question, so I can maybe go to one of these examples. So we have learning building thermodynamics using neural ODs, or resistance capacitance network with neural ODs. There is also this learning to control. So there are different approaches, but essentially, yes, we want to approximate the heat transfer to the building structure. So we either use black box function approximators like neural ODs, or we use gray box, and we estimate these resistance capacitance lumped parameter models in this form. Yeah, so it's basically graph neural net with the kernel is not multilayer perceptron, but it's this 1 over R C linear parameter. So this type of network models are very good priors for modeling heat transfer in buildings. Then when you have this model, you can learn to control the temperature in the building. So this would be the differential control approach. So once I have the system model representation, that will take my control actions that are typically like what is the supply air temperature or supply water temperature in the heating system, and what is the mass flow in that heating system. That's the control actions. Then we have current state measurements. What are the temperatures in different discretization points of this RCnet? And we have also very often disturbances, which are uncontrolled inputs, like ambient temperature or occupancy patterns that can be embedded into the model. Very often we don't know these effects, so they are typically combined with black box function approximator neural network. So you have some gray box component or the resistance capacitance network, and you have some black box or the ambient temperature or occupancy patterns, and you have white box component, for instance, for that input heat flow equation, which is just convective heat flow. We know the expression for that, so we don't need to learn that. And that's your physical model. And when you combine it with neural network control policy, that is taking the measurements of all of these system parameters into desired control action. So what should be my mass flow? What should be my supply temperature for different rooms in the buildings to satisfy the comfort constraints in terms of the temperature evolution and minimize the energy use. So you could formulate this as the parametric optimal control problem. So here I'm tracking the reference of my states, which are the temperatures. Very often in control, we have some kind of terminal penalty, like what is the temperature that we want to achieve after certain time steps. And you are solving this subject to your system dynamics model. And this, we mentioned, it can be this gray box resistance capacitance model or neural OD. And you want to train this neural net that is sampled over the parametric space of this problem.
So then question. So I have let's say a concrete instance of this. So I would prefer to use not my own building model. I want to use Energy Plus, the standard DOE, differential equation, but it's not differentiable. It's just a bunch of Fortran or Python, but it's not in a clean format. So how can I start approaching this, like using established models of phenomenon X to, I have a few use cases. I want to control a building. I want to infer the building structure installation from measurement data, exactly your use cases, but it's not already differentiable.
Yes. So you would need to decide what architecture of your system model you want to start with. Here I have linear state space model, and I would need to go first with the system identification. So
yeah,
let me open, like, let's say this neural ODE building. I'm going to skip all details. There's a lot of like prior work. So I assume like, okay, I have some measurements of the building model, and I'm going to chunk this into the rollouts, and I'm going to, in this case, this encoder decoder with, well, it is a latent neural OD model. Yeah, you have encoder for observables, and in latent space, I trained in neural OD, and then I project it back to the observable space. I'm just skipping the details. This is overall problem formulation. But I would train this model from the simulation of the energy plus, or from the measurements of the real building. So I obtained this differentiable surrogate model of my dynamics that I want to control.
Mm-hmm.
And then I would take this dynamics model that approximates the system to the satisfied accuracy over the long rollout in this optimal control problem formulation.
Got it. So then you do have a differentiable model because you've created your surrogate.
Yes, exactly. So you scroll down, then you should obtain some train control policy that is parametric. So when you will be changing the control constraints and different weight factors on the energy minimization, like you would be obtaining different control trajectories here.
Good. Now, if you specify the input at the beginning, it runs. That's clear.
Mm-hmm.
You have traces. How do you account for control? Like, it's a controllable building in this case. Do you just have a bunch of boundary conditions of all the control points, even as they're being like interactive? Like, it's hot, people adjust. So it's a kind of a biased data set. Is that a problem?
So if I understand correctly, like you're asking, like, how are we training these control policies, and then how are we doing this sim to real transfer? Like, how are we doing it?
I guess it's easier to visualize this when you have all the inputs are given up front. Like, give me this building in steady state forecast. But if it's an interactive thing, like a robot, like a building where people fiddle with the AC, where the use cases, the ultimate use case is RL. A differential model has to account for user interactions, which are not bad in the sample. They're autoregressive. Is that a big challenge or just a minor detail?
It is a challenge if you don't know the parametric space that will be encountered during deployment. Very often in applications like energy systems, we know the operation range of our temperatures. We know the operation range of our controls. So we can train the control policy that is within the distribution. So we cover the encountered distribution, that there is no distribution shift. But if there is distribution shift, let's say we train this control policy to operate between 18 to 25 degrees centigrade. But suddenly the building is in 30, 35 degrees centigrade for some reason. There is no guarantee that this will work because we didn't train there. So the distribution shift is a technical problem that would need to be solved with active learning. You would need to gather more data and retrain the policy to cover that region of the parametric space.
Got it. And then one more, maybe software issue. How is parallelism handled? Because this seems like it's a very resource intensive kind of procedure. Yes.
So for the reason we embark on integration with PyTorch Lightning. So there will be like these examples, like how to use multiple GPUs and using Lightning Trainer. So it would be your standard PyTorch experience using PyTorch Lightning in terms of using GPU support and multiple GPUs for scaling to large models.
Got it.
Yeah, and in our experience, like this Lightning is way more performant than our custom trainer. So in the future, we will probably refactoring all our examples and just use Lightning by default because it's just way better.
Okay, no, that makes a lot of sense. And as they move to more hardware architectures, you're taking along for the ride.
Exactly. So that's why we chose PyTorch, because there is a wonderful community and there is like a lot of development already invested in this ecosystem, and we are building on top of that. We don't want to reinvent the wheel because we are a small team, so we want to focus only on those PIML components.
So actually, expanding beyond maybe the PyTorch ecosystem, it seems like all that you really need is a piece of software that gives you gradients. You don't really care where they come from. So if I gave you like a VM that like I call my code, I return back the response and the gradient with respect to your suggestion.
Yes.
your infrastructure works exactly the same. Is that fair?
Yeah, exactly. It'll work. Like if it is not implemented in PyTorch, you will need to like wrap it. But yes, all you need to have is a forward pass and backward pass, because like all of our components in this computational graph, in this problem, are NN modules.
Okay, and that's where JAX or AutoGrad might fit into this framework.
Exactly. Yeah.
All right. Well, yeah. Thank you. Do you have any concluding things, or?
Yes, I do. Let me go back to the slide. So, okay, I skipped this summary. I can just wrap up that, yeah, this learning to optimize, learning to control, learning to model with neural operators, and learning to solve partial differential equations with physics-informed neural networks. From my perspective, they are conceptually related problems. They are not exactly the same in terms of the theory and detailed technical implementation, but on a high level, allow to implement this scientific machine learning framework that is using unifying abstractions. And I believe that's something that can promote usability and transferability of the ideas from one domain to another domain. So that's why we invested into this API. And I want to acknowledge all my wonderful colleagues at PNNL that I had the privilege to collaborate either on the development of the software or on research of the methods itself. And as a final slide, I have some advertisement of a new group at Hopkins that I will be starting in January at the Department of Civil and Systems Engineering. So I'm hiring multiple PhD and postdocs. So if you know about someone who is interested in scientific machine learning for dynamics optimization control, particularly for sustainable energy systems, please forward them these opportunities. So thank you very much, everyone.
Well, thank you very much. Have a great rest of your day.
Thank you.
Bye.
Bye-bye.